Welcome back, everyone. So today we're going to follow up talking about critical points and how to determine, maybe not graphically, maybe in some computational way, whether a critical point is a candidate for a minimum or whether a critical point is a candidate for a maximum. So we'll be introducing two computational tests, which are called the first and second derivative tests. And we'll be practicing using those to classify critical points. So the first of the derivative tests, appropriately named the first derivative test, says, okay, so suppose you have a function f of x, and you already know that this function has a critical point at x equals a. Now you're trying to figure out, does this critical point correspond to maybe a minimum or maybe to a maximum? The idea of the first derivative test is to check out what's going on with the first derivative of f of x in the vicinity of x equals a. So if you take the derivative of f of x, f prime, if this is negative left of a and positive to the right of a, well, first of all, let's quickly do a sketch of what that might imply. If f prime is negative, then the function, the original function, is decreasing in that region. So it'll look like it's going down. Then if f prime is positive to the right of x equals a, then the original function f of x is increasing to the right of x equals a. And so in the vicinity of a, the original function f of x is going to look a lot like what we have here in green. Now from the picture you can tell that if the function has this behavior, then x equals a is going to correspond to a minimum location. It may not necessarily be the global minimum of the entire function. As a fact, f of x may not even have a global minimum, but at least it's going to be a local minimum. F of x has a local min at x equals a. Conversely, suppose that you take the derivative of your function and you find that the derivative is positive slightly to the left of a and negative afterward, negative to the right. So in that situation, what is the function f of x doing? F prime is positive to the left of x equals a, so the function f of x is increasing on that region. And f prime is negative to the right of x equals a, so the function would be decreasing on that region. So graphically we can tell that the location x equals a should in this case correspond to a local maximum. So someone is investigating the function f of x equals x minus 3 squared, x plus 2, x plus 7 squared. Now someone has already gone ahead and calculated the value of f prime of x for us. Although it is possible to do it by hand, using just really the product rule and the chain rule, it is a little bit tedious. And in particular, it's especially tedious to try and factor f prime back out. So I've just gone ahead and given us the value of f prime of x, completely factored. So part A, let's find the critical points of, I gotta be careful now. Find the critical points of the original function. That's what this should say. Find the critical points of the original function. In order to do that, we need to find the locations at which the derivative of the original function, f prime, is equal to 0 or undefined. But because this is just a polynomial, I can tell that this f prime will always be defined. So now let's use zero product property, which says that if this big mess is going to equal 0, then there are really only three possibilities. Only either the factor x minus 3 can be 0, or the factor x plus 7 can be 0, or the quadratic factor x squared plus 4x minus 1 can be 0. Now the first possibility corresponds to x equals 3, then x equals negative 7, and to determine what's going on in possibility number 3, this is a quadratic equation, so we'll need to use quadratic formula. Negative 4, either plus or minus 4 squared minus 4ac all over 2 times a. You can simplify this if you like. This can be reduced to negative 2 plus or minus root 5, if I recall correctly. Okay, so we have obtained 4 critical points. One of them at 3, one of them at negative 7, one of them at x equals negative 2 plus root 5, and one of them at negative 2 minus root 5. So now let's get into the good stuff. Let's use the first derivative test to classify all 4 of these critical points of f of x as either a local minimum, a local maximum, or potentially neither. When I'm using the first derivative test, my preference is to set up a sign chart. I'm going to create a chart, and what that's going to look like is it's going to start with a number line. And on the number line, I'm going to put all 4 of the critical points that we found in part A. So it looks like the smallest of these critical points is probably down here at negative 7. I think that the next smallest is given by negative 2 minus root 5, whose value is approximately negative 4.2. The next one I think is negative 2 plus square root 5, whose value is approximately 0.2. And then we have x equals 3, the final critical point over here on the right side. All of these are locations where the sign of f prime is given by 0. Locations where the first derivative is 0, so locations where the original function is flat. So what I'm now going to do is I'm going to determine the sign of f prime of x at the regions in between these critical points. And I'm going to do that by picking some test value of x in each region. So for example, to the left of negative 7, I might pick a test value of minus 8. I might pick in the second region, for example, between negative 7 and negative 4.2, maybe negative 5. Here between negative 4.2 and positive 0.2, I might pick 0. Between 0.2 and 3, maybe 1 will be nice. And to the right of 3, maybe 4 will be nice. If you remember the idea of sign charts for solving polynomial inequalities from pre-calculus, it's basically exactly what I'm doing here. So now that I've picked my test points, what I'm going to do is I'm going to plug them into the first derivative to see if the first derivative outputs a positive value or a negative value. Now I just did that via calculator. All that I did was I took these 5 different x values, which I chose in these 5 different regions, and I went ahead and plugged them in to the formula for f prime of x that was given to me, this formula right here. But that's just some calculator nonsense, So I went ahead and did that off screen, and the results of that are right here. So I plugged in -8 to f prime, and I got a positive result. So I'm going to put a nice prominent plus sign on my chart. At -5, I got a negative result. So I'm going to put a minus sign on my chart. Then at 0, a positive result. Then negative. Then positive. So in this case, it's a little interesting. We ended up perfectly alternating between plus and minus every time we crossed a critical point. But do be careful because that's not guaranteed to happen. So what is our original function doing, roughly speaking? F with no prime. F of x is increasing for a bit, and then we reach x equals -7, the critical point at -7, and then suddenly the function switches to decreasing. The function is decreasing for a while until we hit this critical point at -2 minus √5. And then the original function begins to increase again until we hit -2 plus √5. Then the function starts decreasing again until we hit 3. And then the function starts increasing again. So based on this, and based on the first derivative test, what would we conclude? We would conclude that the function has a local min at these 2 points down here, -2 minus √5 and +3. The local maxes are located at positions where we have -7 and -2 plus √5. Now, if you are using the first derivative test, there really aren't any shortcuts that can be used to bypass this sign chart business that we did in the previous problem. And to show you sort of a wide variety of things that can happen, let's consider the function f of x equals x minus 1 quantity cubed. Find and classify the critical points. So if I calculate f prime of x, because this time it's not given to me, the outer function is the cube function, whose derivative is 3 blank squared. Fill that with x minus 1, and then multiply by the derivative of x minus 1, but that derivative is 1 and it won't change anything. This quantity is always defined, so let's set this equal to 0. Now this expression is only equal to 0 at one possible location, the location where x is equal to 1. So this is our only critical point. So x equals 1 divides the number line into two regions, one to the left of 1 and one to the right of 1. Suppose that I pick the test point x equals 0 and maybe the test point x equals 2 to fill out the sign chart. If I plug x equals 0 into f prime, then I get 3 times -1 squared. There's its square. And that evaluates to 3, which is a positive number. But if I plug in my second test point, f prime of 2, that's 3 times 2 minus 1 squared, which is still equal to 3 and is still positive. So, the function is, the original function f of x is increasing to the left of x equals 1, and just carries on increasing after going through x equals 1. So in this particular problem, x equals 1 is neither a local min nor a local max. If we look at the graph of f of x, this does make sense. The f of x in this problem is just a horizontal shift of the function x cubed. So although the function is technically flat at x equals 1, that point does not represent either a local min or a local max. We can get a slightly less tedious solution using a different technique, which is called the second derivative test. Now, just as the first derivative test concerned the first derivative, the second derivative test involves the second derivative. So, say that we have a function f of x, and we already know that it has a critical point at x equals a. And what we would like to do is we would like to determine whether the function has a local min or a local max at x equals a, or possibly neither, as in the previous example. Suppose that you take the function's second derivative, f double prime, and plug a into that. Plug the critical point directly into the second derivative. If the result of that is negative, then the function has a, are you ready, a local max at x equals a. Now it might seem a little bit backwards to get a negative output from the second derivative and then have the original function have a local maximum. Somehow, in my mind, I tend to associate negative with low stuff. But what's happening here is that when we say the second derivative is negative, then that means that the original function is concave down. Concave down from back when we talked about concavity and inflection points in, I think, video 15 or something. So if a function is concave down, it looks a lot like this quintessential concave down negative parabola function. It looks a lot like this. And so if the function is concave down, and the function looks like a bowl that is tipped upside down, then the critical point A, where the function is flat, is located at the top of the bowl. And so it represents a local maximum. Concave down, local max. When in doubt, I recommend to just draw a little sketch to help you to remember. Concave down looks like a parabola opening down, and so the critical point is a local maximum. Conversely, if you plug the critical point into your second derivative and get a positive number, then the function has a local min at x equals a. Why is that? Well, if the second derivative is positive, then the original function is concave up. And so it's going to look a lot like this right side up bowl, like a right side up parabola. And the critical point in that case is going to be at the bottom of the bowl, and therefore is going to represent a local minimum. So I generally try and remember this picture. F double prime positive means function is concave up, means the point is a local minimum. Now what if neither of these two things occurs? What if you take your critical point, plug it into the second derivative, and get 0 on the nose? If you get 0 on the nose, you're unlucky. You're going to have to use some other method, some other test, to classify the critical point. Because second derivative test tells you absolutely nothing at all about what's happening in this situation. If f double prime of a is equal to 0, then second derivative test is no good and cannot help you at all in that situation. Anything could be going on and you have no way of knowing except to investigate by different means. So let's get some practice using the second derivative test. in this situation. We've got f of x equals x minus 2 times arctan of x. Let's start by calculating the value of the first derivative, f prime. So the derivative of x is 1, and from our work on derivatives of inverse functions, we remember that arctan x becomes 1 divided by x squared plus 1. So let me just clean that up and put 2 in the numerator. Find the critical points of f of x. Now in this case, f prime of x is not a polynomial. It actually has a denominator with variables in it, which means there actually is a chance that this function could be undefined at certain locations. For example, we know that we can't divide by 0, so we should check if x squared plus 1 can ever become 0. However, such a thing would require x squared to be equal to minus 1, but since we're only dealing with real numbers for x, this is not possible when x is a real number. So this function, f prime of x, is always defined. So kind of as usual, our main objective is to take f prime of x, set it equal to 0, and solve. Oh, and folks, I'm just noticing this typo up here. This should of course be a minus sign from the minus sign in our original function. So having fixed the typo, let us now proceed to figure out which values of x make f prime equal to 0. Almost did it again. Oh no. Minus 2 over x squared plus 1. If I just rearrange this a little bit, maybe move 2 over x squared plus 1 to the other side, and clear the fractions, then this says that if x squared is equal to positive 1, so that x itself is equal to plus or minus 1, then the function x minus 2 arctan x will have a critical point. And these two values are the only critical points. So let's go ahead and let's classify those critical points using the second derivative test. So in order to use the second derivative test, we're definitely going to have to find the second derivative. And just so that I can escape having to use quotient rule, I think I'm going to rewrite the first derivative in the following way. 1 minus 2 times x squared plus 1 to the power minus 1. So now when I calculate f double prime, the 1, the constant 1, vanishes. We have that negative 2, but now for this back quantity I can use chain rule, which says take the derivative of the outer function, which is negative 1 blank to the power negative 2, fill the blank with the inner function x squared plus 1, and multiply by the derivative of x squared plus 1, which in our case would be 2x. So f double prime of x could be rewritten as, it looks like, positive 4x divided by x squared plus 1 squared. So now let's investigate what's happening to this function at the critical points. In second derivative test, we don't have to worry about what's going on around the critical points. We only have to check what's going on at the critical points. So, at the critical point x equals positive 1, what is f double prime doing? Plug 1 into this formula and you get 4 times 1 over 1 plus 1 squared positive 1 it looks like, which is certainly a positive number. Now let's remind ourselves that this means that the original function f of x is concave up around x equals 1. So what is x equals 1 actually? X equals 1 is the location of a local minimum of the function f of x. Then basically the opposite thing happens. In this case, f double prime minus 1 is equal to 4 times minus 1 in the numerator, minus 1 squared plus 1, quantity squared in the denominator, result negative 1. So in this case, the original function is concave down at x equals negative 1, and we would say that f of x has a local max at x equals negative 1. But there is one huge drawback to second derivative test. If it were not for this one drawback, it would probably be my favorite test. But the issue is that, on occasion, second derivative test just completely fails and doesn't tell you anything about the function. Let me give you an example here. We have f of x equals x to the 4th power. Find and classify the critical points. So in this case, f prime of x is equal to 4x cubed, which is always defined. And so in search of critical points, I'll set this equal to 0, and it says x equals 0 is a critical point. Now, in my attempt to use second derivative test, let me calculate the second derivative. But if I plug my critical point into that, then 0 is the result. But that in and of itself does not tell me anything about the actual behavior of the function around x equals 0. Let's switch to first derivative test to see if we can get any more concrete information. So let me set up my sign chart. We have x equals 0 in the center. So maybe I will pick the test locations minus 1 and positive 1. So if I plug negative 1 into my first derivative, I get 4 minus 1 cubed, which is a negative number. And if I plug positive 1 into my first derivative, then I get 4 positive 1 cubed, positive 4, and that's a positive number. Which means that my original function must be decreasing to the left and increasing to the right of x equals 0. And from first derivative test, I now know for sure that x equals 0 is the location of a local min. So even though second derivative test is, generally speaking, a lot more convenient and swift, it is just not quite as reliable, and in certain cases like this one, doesn't give you the complete picture of what f of x is actually doing. Okay, that concludes today's material, talking about computational ways to determine the behavior of a function at various critical points. We introduced the first derivative test, which says what is the sign of the first derivative to the left and to the right of the critical point. And then we introduced the second derivative test, which says what is the behavior of the second derivative at the critical point.